So previously we defined the underlying concept in an experiment that illustrated what was known as spin. And the experiment that we went over was what was known as the Stern-Gerlach experiment, right? And the Stern-Gerlach experiment actually illustrated a very curious phenomenon. A very interesting thing, where if you took a magnet, right, and essentially the apparatus itself can arguably be seen as a gigantic magnet, right, where one point on the top is made a little bit pointier, right here. Let's see if I can circle that. It's made a little bit pointier, and that actually makes the strength of the magnetic field as these particles that we're firing pass through the apparatus, makes it a little bit stronger, so that particles that are attracted to whatever pole is at the top will actually be deflected arguably upwards, and those who are less attracted will be deflected downwards. And as we showed last time, what the results of the Stern-Gerlach experiment ended up having was that these particles that we fired through, in this case we considered electrons, the Stern-Gerlach experiment, the initial experiment actually used silver atoms, would group these into one of two categories, up and down categories. And that's where we stopped. That's where we wanted to consider precisely what we had on our hands. And so there are a number of misconceptions that we do have to address going forward. But first of all, let's understand the concept of spin by breaking down this experiment that we have before us. So let's talk about what spin is not. So spin is quite an unfortunately named characteristic of subatomic particles. Contrary to what it says, it does not mean that these particles themselves are actually spinning like you would have an Earth on an axis. However, if you look up the Google definition, if you look up the Wikipedia definition of spin, you'll see something along the lines of intrinsic angular momentum. Intrinsic, and I cannot spell, intrinsic angular momentum. Right, for some sort of very for some sort of very small particle that we essentially have. And so let's break this down a little bit more, right? So the definition itself contains three primary words: intrinsic, angular, and momentum. And we'll start with the momentum. Maybe if you've taken classical physics before, if you've taken a general 1D motion, 2D motion, you might have heard of what is known as momentum. And momentum, in this case, angular momentum, is not quite the same thing as that same concept you encountered earlier. You might have encountered what is known as linear momentum, right? Linear momentum. And in this case, linear momentum is, and this, explain it by way of example. Let's say you have a car, right? A green car. And if it's moving anywhere, if you have this car and let's say it's driving this way, oh, that's a very strange place to put a window in that case, right? So you've got a car and it's going in this direction. And so in this case, what we have here is a case of movement. And in this case, it has a velocity. And momentum is defined as mass by velocity for linear momentum. And on the other hand, what is known as angular momentum, right? Angles. It suggests there's some sort of spinning occurring here. And so in terms of angular momentum, that is just the momentum we have when you have something like a particle spinning on an axis. Right? And let's make this axis a different color. You have some particles spinning on an axis, or on the other hand, you might have something kind of going and orbiting around another object, much like how the Earth might orbit around the sun. And so that's basically what angular momentum is. Now, these two examples here we have defined are rather physical, observable characteristics and instances of something that an object is doing. But then when we add on and we tack on this description of intrinsic, that actually changes precisely what we're considering. And so let's dig a little bit deeper, all right, and let's consider what intrinsic means. Intrinsic. And so intrinsic, and you may have heard this before if you've ever taken chemistry, for instance, actually is paired up with extrinsic. And these describe characteristics. of a given object or a given item characteristics, right? And so with that in mind, let's give a few examples. Characteristics, right? So an example of an extrinsic characteristic might be that we are considering something like mass, right? So in this case, an extrinsic characteristic depends on, how much of a given object, how much of a given substance that we have. The more apples that you have, the greater mass of apples that you have, because you have, 2 objects in this case to consider. Now, when we talk about intrinsic characteristics, this would be something similar to density, right? Which is mass divided by volume, or charge in this case. So, for instance, an electron has a negative charge. And so in this case, an intrinsic characteristic, just to briefly define it, is essentially something that a particle has or an object has that does not rely on its quantity. Now let's consider and wonder, where in the world does spin go? Right? What does spin fall into? Now, as we said before, it's defined as intrinsic angular momentum. So it does, in fact, go in as an intrinsic characteristic, which means that electrons, for example, can either have a spin of up or down, or might have protons, or might have neutrons that have a spin associated with them. So no matter how many neutrons you have, there is still some degree of associated spin with each individual neutron. So let's go a little bit further, and let's consider precisely how this ties into what we said earlier about the Stern-Gerlach system. Stern-Gerlach experiment. And by doing that, let's first consider experiment. Why an analogy in classical physics, right? A classical physics analogy. So this is not exactly what spin is, but classical physics analogy to kind of illustrate what we have on our hands. And to start off our classical physics analogy, let's start by drawing this apparatus that we have here. Right, and just to reiterate, it's just technically a giant magnet that we have on hand. That should be a flat surface. Right. And when you send a particle through it, let's take it from the classical physics perspective. Alright, and so let's say we have some magnet here, some tiny little bar magnet, and it's oriented in such a way so that red is on the bottom and blue is on the top, so on and so forth. And so if we send this particular magnet right through here, right, if we take it and we send it through, what would happen is, because your red, your pole, your north pole in this case, we'll call this north, and this down here is south, because it's sharp, quote unquote sharp, but essentially its magnetic field in this case is going to be stronger. This little bar magnet here is going to be deflected upwards. Now on the other hand, if we're considering another bar magnet, right, a bar magnet that is in the opposite direction, such that you have red on top instead, right, and blue on the bottom, ideally, according to what we said earlier, this would be deflected downwards. Right, deflected downwards. But here's an issue that we kind of run into rather quickly, which is what happens if we send in a magnet such that it is laying 90 degrees on its side, right, in this way. Now, if we were to take it as a typical everyday bar magnet, what we would say is, alright, what we want the Stern-Gerlach experiment to fundamentally do is not have any effect on this little bar magnet at all. But if we were to take it from the classical physics perspective, if we were to consider what we said earlier, which is that this, right here, has a stronger magnetic field, then in that case, that would just mean that this little bar magnet that we have here is going to be deflected and turned around so that it can actually fit whatever orientation that we have here. And that's a major issue because we don't want this apparatus that we have here actually interfering with our experiment, because following that same convention, every single magnet that we send through there, no matter if it's oriented in this current direction or if it's oriented in the opposite way with red on top, is always going to be end up turned around and flipped, right? Such that it fits this ideal perspective for a Stern-Gerlach experiment, and that is an issue that we want to address. And so as it ends up, this isn't actually a problem with quantum physics, and this isn't actually a problem with the actual Stern-Gerlach experiment, and the reason here lies in what we defined earlier, in this intrinsic angular momentum. But since we're doing a classical physics analogy, we're going to be taking the extrinsic, not necessarily extrinsic, but we're going to take actual physical angular momentum. And so let's erase what we have here, right? And let's start by defining what this angular momentum of a typical particle is. And so in this case, we have, let's say, an electron, right? Or just some particle overall. And in this case, the angular momentum that we want to consider with classical physics is that it's physically just kind of going around in a bit of an orbit. And so this is its axis, right? Its axes. And in typical physics, the way we determine and we describe the direction is by having an arrow parallel to the plane on which this particular particle or object is rotating around. Perpendicular to the plane. So if this is the plane, right, then it's perpendicular to it. Now, what's curious, though, is that this angular momentum, right, and is going to, much like how you might have considered linear momentum, is going to actually create some resistance to actually being flipped. So if we stick it back into our Stern-Gerlach apparatus, and we take a particle that has some sort of angular momentum, and in this case, since once again we're considering the classical physics perspective of it, if we stick it in there, right, turn very small, alright, and if we put it in there, and let's say the ideal direction, here, let me redraw this. The ideal direction, in fact, would be, say we have a particle that is going around, right? And let's say its current direction is this way, and the ideal direction that we do want it to have is like this. Now, what your apparatus might attempt to do, if we were to follow the line of classical physics, is that it might attempt to take whatever particle we have here, right, in this case, this lovely little orbit right over here, and it might attempt to flip it again. It might say, okay, I want you to flip so that your direction is pointing upwards. But the thing is, that creates a change in angular momentum, in the direction of angular momentum. And it's worth noting on the side that angular momentum itself, angular momentum, much like linear momentum, is considered what is known as a vector quantity, right? So it has a sort of direction applied to it. And so in this case, it's going to try to flip it, but when you have that change in angular momentum, essentially your particle is going to say, hey, I don't want to be flipped. I'm going to resist that, and I'm going to try to pull back. And what ends up happening is, instead of having a particle that's spinning, directly on this axis, you end up having something that it looks like this. So you have a particle, right? You have a particle, and you have its orbit, and then we draw the particle in, right? And its axes of rotation, actually, because there's something that's trying to turn it, ends up tracing out something that looks a bit like a circle, right? And this phenomenon here, so this axis is going to kind of change a little bit. It's going to wobble almost a little bit, in a sense, it is what is known as Larmor, let me capitalize that, what is known as Larmor precession. Keep in mind, once again, this is still the classical physics analogy that we're doing just to illustrate spin, but here's the thing, if we send something like an electron through this Stern-Gerlach apparatus, it does something very similar, right? It resists being changed and turned and having its spin, in this case, completely changed so that it only goes in one direction. It resists that, and so that's where our analogy comes in. That's where the concept of angular momentum comes into play, and that kind of lays the foundation for much of it. Now, it is, once again, worth noting that was, an analogy, right? So spin. Now, after clarifying a lot of this and its unfortunate name, let's talk about this intrinsic angular momentum. It is worth noting that electrons themselves do orbit. Let me use a different color. Do orbit around your nucleus. They not orbit, but they do exist in orbitals and electron clouds around your general nucleus, right? They kind of go around. And the thing is, spin is actually, so this itself has some sort of angular momentum. So it has some sort of angular momentum, right? But spin itself kind of adds on to that, plus spin, and that is your total angular momentum for your given particle. And because the electrons, once again, like we said in our earlier instance of the Stern-Gerlach experiment, as we described, because it resists, wanting to change, we finally have this angular momentum. But the electron itself is not actually spinning on the little axes. That's why it's intrinsic. That's why it's known as being an inherent property of this particle. Of course, if you want to argue a little bit further and consider why it's intrinsic, keep in mind that, for instance, neutrons have spin. Right? Neutrons have spin. But the thing is, this description, an electron rotating on an axis, actually gives it some sort of electromagnetic field, gives it some sort of field, but neutrons, here's an electron, right? But neutrons, when they rotate, claiming that they will exert some sort of field, some sort of magnetic field, it is a little bit of a stretch in that sense. Alright, so now that we have technically defined spin as being inherent angular momentum, let's consider what that means in the context of everything else.